survey. It's actually not 20, it's 20 plus. There's 22 questions. Should be pretty short. It will open today at 4:30, and the deadline is on Friday. Now, to entice you to do this survey, I will give you some benefits for doing it. Okay? So what I'm going to do here is that for assignment 4, I'm going to post 2 of them. Okay? So there will be 2 assignment 4, and for each of them, the MRQ mark, so the select all, the applies kind of thing, will be marked immediately through the system, but without the partial marking. Okay? So, yeah, so you will see whether you get either all the answers are correct or some of it is wrong. Okay, so that's the kind of feedback that you can get immediately on assignment 4. Okay, so if you do the survey before the deadline, of course, then I will take both of your mark, and then I will just choose the highest one. Okay, so I'm allowing you to redo the assignment, basically. So yeah, that is the benefit to entice you to do the survey. Okay, so please try to do the survey as truthfully as possible. The only slight problem is that it cannot be fully anonymous. Okay, it is some problem that I face because here I need to know that you have done the survey. And what we are doing here is that the assignment 4 is not using the same system as the survey. Okay, so I need to connect the 2. Okay? So what I'm going to do is I'm only going to get your student number from the survey, and it will not implicate you in any way. Okay? You will not get penalized for whatever remark you put in the survey. It's just a slight little snag in the system. Okay, so please try to be as truthful as possible. Assignment 4 will be released this Sunday. And the important thing will be that the website, the Heroku, will be closed on the Saturday. Right, so next week, tutorials, if you want to do it, I'm going to release the tutorial early. If you want to use the website, then you have to use it before the Saturday. Right? Just to make things very, very clear for assignment 4, the last download, the last time you can download the assignment on Exemplify will be on Friday, 8th of November at 11:50 p.m. So even though you may not want to do it at that time, please download it first. I need to set the last download time. The deadline will be on Saturday, 9th of November. So let me double check all the dates. Today is week 10. Next week is week 11. So the deadline will be on the week 12. Okay, so just remember that you also have the project report on that week. It might be useful to start early. Okay, so that's for the surveys and assignment 4. The assignment 3 and the midterm marking is still ongoing, but they should both be finished by end of the week. Because this is a programming assignment, and the midterm is also for programming, I will run plagiarism checker. Okay? If you are found to have plagiarized but you did not admit, you get reported to the RO. So I'm giving you about a week to admit that you did some kind of plagiarism. Now, if you do admit, then you only get the minimum penalty, which is you get 0 mark for whichever assignment or midterm you are plagiarizing. So the deadline for the admission is on the 24th of October. By then, after that, I will then run the plagiarism checker. Okay, so if I found any plagiarism, which you cannot explain, then I will have to report it to the registrar. Okay, so just to make things clear, I already did say what constitutes as plagiarism in the lecture 0, which is for the admin part. So it's this particular page that I retrieved from the lecture 0. So even if you are the one giving the code to your friend, it will constitute as a plagiarism because you are aiding plagiarism. Okay, so we are very, and US is quite strict on this. Okay, so please report to me by Thursday or to your tutor, okay, during the tutorial. All right, so that's basically for the announcement. Since a lot of you are now here, let's start with lecture 10. This is kind of your last examinable material. This after this, there's no lecture next week, and the week after that is I'll see if I can understand NoSQL completely by then, and then we will have NoSQL. Okay, I'm still quite lost about what NoSQL is. Week 13 will be review. So the last two is non-examinable, but if you want to know the latest trend in database, then it's useful to come. Okay? You can also use the time to do your project if you want, because again, these are non-examinable material. Okay, so normal forms. Okay, so we have decompositions. This is a summary of the decomposition, which is that every fragment should be simpler, and then there are no attributes missing. It corresponds to a projection operation. Because in this projection, if you do the natural join, we can then define a lossless join decomposition. If there is nothing that is missing. So if you can get back the original information, then it's a lossless join. We do have a lemma that says that your natural join will definitely be larger than your original one. Okay, so it's larger or equal to. So it does not mean that lossless join will remove rows from the final relation, but it will actually add more rows to it. Corollary 1 is very useful. If you have a completely non-trivial FD, you can decompose on that. All right, and that is because based on theorem 1, yeah. Okay, so because based on theorem 1, if you have A to B here, this one, you do R minus B intersect with AB. The only thing that you can get is just A. Okay, so you get B here removed, so the only thing that you will get is A. Now obviously, this will be A to AB. We will naturally apply A to AB because you create this based on A to B. Okay, the AB is exactly your R2. So you have A to R2. So it's automatically, if you do the decomposition this way, this will be automatically lossless join. And this is the kind of property that we abuse later on when we do the BCNF decomposition. Theorem 2 is just basically to find a lossless join decomposition from an arbitrary number of fragments. Okay, so, and then we have the dependency preserving decomposition, and we need this simply because we do not want to check from the join. Okay, so we need to be able to check all the functional dependencies before we even perform the join. So yeah, so if it is a dependency preserving decomposition, then you can do the functional dependency checking before you perform the join. So only on each of the fragments. And then we have 4 algorithms. The first algorithm is to find attribute closure. Second algorithm to find the minimal cover. third algorithm will be to find the projection. Algorithm 4 is to check whether it is a dependency preserving decomposition or not. We have no algorithm to check for lossless join decomposition, but there is actually an algorithm. I forgot the name. So for lossless join, what I want you to do is to check whether it is a lossless join decomposition. What I want you to do is find a series of decomposition. So you have the R intermediate. Okay. If you can find a series of decomposition such that each of them is a lossless join decomposition, then based on theorem 2, you get a lossless join decomposition on the final fragment. So this is the final fragment. Okay, so let's have a preliminary first. What is a normal form? Okay, so the normal form kind of supposed to involve a feeling of that certain things are abnormal. Okay, but what we mean by normal is that we do not want to have any anomalies at all, or the anomalies is as minimal as possible. When we talk about the strongest form of normal form in this module, which is what we call the BCNF, then you are guaranteed that you don't have any of these anomalies. Okay? This normal form only works on certain kind of database. Okay, so there is the kind of database that we call a relational database. The first property of the relational database is that every element, so the tuple, which is the A, B, C, and so on. The first property is that this one, each of these, must be atomic. Right? And there is actually this thing called the first normal form, which says that exactly this. If each of your element is an atomic element, that means there's no table within a table, then you have the first normal form. Okay, so by default, everything is already in the first normal form. Okay, and then we get stricter and stricter from there. Now, instead of going through this from the bottom up, making things stricter, we try to do this at the top-down level. We try to figure out what we want at the end, which is the BCNF. Right? So we start from BCNF, and then we try to relax the condition slightly because the BCNF is too strong. Certain things cannot be decomposed into a BCNF. The Boyce-Codd normal form. So we need to find something that is more relaxed, and that is the third normal form. Okay, so you can think of BCNF as your 3.5 normal form. However, in total, there are about 10 different normal forms. We're not going to go through all of this because some of this is using a concept that we haven't taught you before, which is the multi-value dependency. Okay, now this is the key idea behind this normal forms. That when you look at occurrences of these anomalies, many of these can actually be traced back to the concept of what is an entity. So that's why we have the ER diagram, the entity relational diagram. If you can form everything as a purely entity and relation, then there will be no problem about these anomalies. But that is the kind of the guarantee that we have. Now, but obviously, we are not talking about all features of the ER diagram. We're only looking at a subset of it. In particular, we don't talk about the total participation constraint because it cannot really be enforced in a table. Okay? So we only look at everything that relates to functional dependencies. The feature of ER diagram that we can relate to functional dependencies is the notion of a candidate key or the primary key, as well as the key participation. It's the key constraint. Okay? So key constraint translates to the foreign key, which is again kind of a functional dependency. And the primary key is a form of a functional dependency. Okay? So here, to prevent this kind of anomalies, you need to make this R1 to be basically either an entity or a relationship. Then you're guaranteed that you do not have this kind of anomalies, the insertion anomalies, deletion anomalies, or the update anomalies. Now once R1 becomes an entity, R2 may not be an entity. Then you have to work on that. In the concept of BCNF, what we say is that when you're doing the decomposition into the BCNF, you figure out that, well, R1 already satisfies the BCNF property, but R2 has not. So we need to find a decomposition of R2 into entities or relationship such that it will then become entity or relationship, which satisfies the BCNF property. Okay? So that's what we want to do in this current lecture. So let's talk about the Boyce Codd number 4. I keep talking about this BCNF, the Boyce Codd number 4, but it is still kind of vague about what we mean by this. So let's look at the definition. This is the definition for the Boyce Codd number 4. So you either have, you look at every functional dependency. To make things simpler, we say that the right-hand side is a single attribute. Okay? It's just to make things simpler, because you can always make it to be combined. Then A must be a superkey. Okay? So it's either trivial, either the dependency itself is trivial, or if it is non-trivial, then A, the lowercase a here, must be a superkey. Okay, now think about it. If the capital A is a single attribute, any trivial constraint means that A is inside lowercase a. Now, the non-trivial means that this is not here, and because A is a superkey, now we have one possible. If A is minimal, then we have a key. If A is not minimal, then we can actually find a minimal one. So we start from this lowercase a. If you keep on removing things, if you keep on removing attributes from the lowercase a, such that we still maintain this functional dependency, then what we have is basically as a candidate key. The minimal a here will be the candidate key. So in the end, if it satisfies this, either you have a candidate key, or it is contained in parts of the, so the attributes here is either a candidate key, or it tells you something about the candidate key. Right? Which means that every attribute within this R, within this relation, is indeed part of the same entity. Okay, so that's what the Boyce Codd number 4 is. It's either part of the entity or the relationship. So that's why this is the strongest. This is what we would expect our database to be. Okay, and that's why we talk about the entity relation, entity relational diagram. So that's the definition of the Boyce Codd number 4. If you want to check whether the relation R, you're going to check whether R violates BCNF, then you just have to check that it does not satisfy this. So what you can do is that if you want to prove that the relation violates BCNF, you say that it is non-trivial. You say it's non-trivial, and it is not a superkey. All you have to do is find one single violation, and that's it. If you find a single violation, then it's not BCNF, then there is a possibility that you should actually decompose this relation further. When we talk about the decomposition here, there's a slight problem, because we say that the decomposition, each of the fragments is, so the decomposition itself is in BCNF if each of the fragment is in BCNF. However, you can always trivially make everything to be BCNF. If you decompose things into its smallest constituent, so every table, every relation consists only of a single attribute, then you do actually have BCNF by default, because everything is trivial. Every functional dependency is trivial. However, this is definitely not going to be lossless join. This is definitely not going to be dependency preserving. Okay, so what you want to do is you want to find decomposition that is still in BCNF, but it maintains, hopefully, lossless join and dependency preserving decomposition. If you can do that, then you are guaranteed that there will be no anomalies, and that is kind of what your database should look like. Right, so again, this is just reiterating that to check for a relation in BCNF, what you have to do is just check for these two things. Okay? Whether there's a violating non-trivial MB. And this brings us to the algorithm to check. So the algorithm, the way to check whether a certain relation R is in BCNF or not is to basically just check either one of these. So you have two possible cases. One, right? So the first case is that Ri here is not from a decomposition. It is not a fragment. It is the entire relation itself. If it's the entire relation itself, then you just check if there is any functional dependency in F that violates the BCNF. However, if Ri is actually a decomposed relation, then some of those functional dependencies may not actually be useful. For instance, let's say I have R here as A, B, capital B, capital C. I decompose into R1, A, B, and R2, B, C. If, for instance, I have this functional dependency A to C, then obviously I cannot check this in any one of them. Right? So we need to check another thing. We need to check the projection instead. Right? So you look at the projection, you look if any functional dependencies in the projection violates BCNF for this particular one. Right? Now, we then go into some little nifty trick here, is that why don't we just put both as a projection? And actually we can. So, if R is the entire relation, if Ri is the entire relation, then what is Fr? Okay, so this, if you project over the entire attributes, what you will get is basically F plus. Okay, so you can just simply ignore the first check. Everything we do is based only on the second check. Okay, so this is the trick that we use, because if Ri is equal to R, so that's the entire relation, then we have Fr, which is equal to F plus. Okay, which is exactly what we want. Now, if there is any functional dependency within this F plus that violates the BCNF, then indeed it is not in BCNF. Okay? So that's the main steps of the algorithm. So before we go into that, let's look at the example. So here I'm asking whether this one is in BCNF. Okay, so you look at each of this. You look at BC, DE, you look at AB. If any one of this is violating the BCNF property, then R is not in BCNF. Right? So if you consider A to B, then we look at the properties. A to B is non-trivial. Okay, so that's the first set of properties. It is non-trivial, and A to B is not a super key. Okay. So then we have found a violation. We found a violation that the proof that R is not in BCNF is because this is non-trivial, and A is not a super key. Right? Because A plus here is AB. Now if you look at BC to D, again the reasoning is still the same. You consider BC to D. Again, this is non-trivial. And secondly, BC plus is equal to BCD. Okay, so this is not the super key. So either one of these functional dependencies can be used as a proof that R is not in BCNF. Okay? Now this is something good to note, that we have two possible candidates as a proof for violation. Okay? And this, in the end, this will lead us to two kind of different decomposition. Okay, let's try another thing. Let's look at this. We decompose R into R1 and R2. Okay, so R2 is ACDE, and just you can see that this is a proper decomposition. This is a valid decomposition. Then the question is R2 in BCNF? Okay, so if you only look at the first step of checking the violation of BCNF, then this is one possible proof that we can use. We say that we consider AB. AB does not hold in R2. So A to B does not hold in R2. BC to D does not hold in R2. And because we do not have any more functional dependencies, then R2 is in BCNF. Okay? This is if you only look at the first step of the checking process. However, this is not complete. This is not the correct proof. Because again, if we are looking at a decomposed relation, if we are looking at a fragment, what we need to look at is this, the projection. So far we have not looked at any projection. We have only looked at F itself. So if you look at the projection itself, then you have to consider AC to D. AC to D is in F plus. Right? And again, AC to D is in FR2, is in the projection. And it is quite simple, so you can just say AC plus, you compute AC plus. Okay, so you have AC, which means that you have A. So you can get B, so you get A, B, C. Okay, so now you have BC, but from BC you can get D. So this is AC plus, ABCD, which means that there is a functional dependencies of the form ACD. And again, we are only interested in the completely non-trivial, so I can always decompose this again into two parts, AC to AC and AC to D, by the extended Armstrong axiom of decomposition rule. Okay, so now we have this, AC to D. If you look at this AC to D, it is in the projection, it is non-trivial, and AC to D is now super key of R2. Alright? So here again you look at AC plus. with respect to FR2, and then you will get ACB. But R2 contains E. E is not here, which means the AC is not the superkey. So this is why R2 is not actually in BCNF. The previous supposed proof is actually a faulty proof, because you have not looked at FR2 itself. Right? So, let's try to redo this. Let's try to redo this step again. But now we only consider the step 2. If we consider the step 2, then we need to look at FR. To look at FR, this is equivalent to F class. A lot of this is going to be purely trivial. CS202, FD and F dot Heroku F. Ah. Ah. Okay, so if you click on this FD projection, you got this FD projection, but you're giving it the entire relation A, B, C, D, E. What you will get is basically F class. So you see there's all of this. Right? But from all of this, you can then prune this out such that you will only look at the non-trivial one, the completely non-trivial. Or you look at parts of it that can be decomposed into completely non-trivial. So these are all trivial, and then you have BC to D from here. Right? So BC to D, you have BC to D from here as well. You have ADE to B. Okay? So what you have to do is you just have to look at those. Right? Slightly more, but it will also solve exactly the same thing. Now the reason why I brought this up is because if you develop an algorithm, then it is actually easier to have one single algorithm instead of having an if statement saying that if it's a relation or if it's a decomposed relation. Okay? So this is exactly the main point about this exercise. We do not have to differentiate because eventually, if you do a projection on the entire relation, what you get is the F class. Okay, and F class will definitely contain, the F class will definitely contain this. So it is the same as if you are checking for this. But now you have a consistent algorithm without branching. All right, so any questions on this? So this is the correct proof. R2 is not in BCNF because you have to look at the projection itself. All right, so now we come into lemma 3. The third lemma says that for any relation with exactly 2 attributes, any relation in 2 attributes is always going to be in BCNF. And the proof is actually rather simple. You have 4 cases. One is that there is no functional dependencies. If there is no functional dependencies, then all FDs are trivial, so no violation can occur. If you have this, then it satisfies BCNF. Okay? Because from A to B, you can get A to AB, which means that A is the super key. Okay, we only have 2 attributes. The same for this, you just have to revert A and B, and the same for both. If you have both, this is exactly all the possible non-trivial dependencies, or all the possible completely non-trivial dependencies. Okay? So you only have 4 possible cases. In all 4 cases, everything satisfies BCNF property. Either because everything is trivial, or the only non-trivial FDs satisfy the superkey property. Okay, so that's lemma 3. Now, with this lemma 3, we can then have a smarter way to check whether things are in BCNF. The smarter way to check is that we try to decompose things. We try to decompose the relation such that in the end we get only the relation with two attributes, because it's guaranteed to be BCNF. Right? So we're going to abuse lemma 3. Right, so this is the algorithm to check for BCNF. You don't have to check for things for relation that have exactly two attributes, because it is guaranteed by lemma 3. Okay, so if you go further, you can define lemma 4. Every relation with one attribute is definitely going to be BCNF, right? Because all the FDs are definitely going to be trivial. But 2 is actually the minimum that you can guarantee. Everything, every relation with two attributes is going to be in BCNF. Right? Now, this is the hard part. Okay, so we need to be able to generate this. Okay? So you generate this FRI. It's good. You use the projection algorithm. I believe it is either 3 or 4. Okay, one of those algorithms. Then you can generate all of you can generate all the projection. So then, once you do that, this set is probably going to be very, very large, because it must include all the trivial functional dependencies. Okay, so if you want, you can try to filter those out first. So look only for the non-trivial functional dependencies. Okay? So if you can guarantee that it's non-trivial, then you just have to check for this. You check if it is a superkey. Okay, so the question is, how do you check if A is a superkey? So again, we use algorithm 1. To check whether A is a superkey, you compute A plus with respect to FRI. And then if A plus is equal to Ri, then A is the superkey. Okay, now, but filtering out the trivial functional dependency is not that easy as well. So this is where we do another trick. So this is the algorithm itself. One part here, in particular line 5, has been highlighted. It is highlighted in both colors. This single line, this very simple check, will actually check for both. We will check for both triviality, or rather non-triviality, and it will check for the fact that A is not a superkey. Okay, so how do we do this? Well, simple, right? If A so what does this one say? Or actually, let's just go directly into that. Let's look at this. What does this one mean? So x comes from A plus intersect with Ri. What it means is that x here comes from the projection. It is basically related to the projection Fri. Right? So the A plus is the attribute closure but you're only interested in the attribute that exists in FRI. Okay? So A to X is some kind of functional dependencies if we say that A is a proper subset of X. The size of A is definitely smaller than X. It means that this is definitely non-trivial. Right? Because you look at the attribute closure, you intersect with Ri, then if A is strictly smaller than X, then A to X is definitely non-trivial. Because if it is trivial, we have this. Right? Okay, so that's for the trivial. So this part checks for non-triviality. This part checks that A is not a superkey. Okay? So how do we know that this is not a superkey? Well, you look at this. Are all the attributes. That means if you look at the attribute closure of A, which is the X here, so if you look at only the attribute closure within this Ri that comes from A, you cannot get the entire relation. You cannot get this Ri because this is strictly smaller than Ri. Okay, so this one checks for non-superkey. Because it means that A is not going to Ri. Right? So this simple check is actually doing both the jobs. Checking things to be trivial as well as checking these functional dependencies to be non-superkey. So the A is non-superkey and this functional dependency is non-trivial. So line 5 here is the major part of this algorithm. And what it's basically saying that is the functional dependency is non-trivial and A is not superkey. Now the first part is this is basically checking lemma 3. Right, this loop is basically checking for all the subsets. Okay? So any questions? Now, then comes the last part. The output of this is a completely non-trivial FD. Okay? So again, this is, well, we say that at this point, if you come to the line 6, which means that the condition is true, what it means is that it is a non-trivial dependency, but it may contain the trivial part. So what you do is you remove all the trivial part. So then what you have is a completely non-trivial functional dependency that violates the BCNF. Line 5 checks for violation. Line 6 remove the trivial part of the violations that is found. So that's algorithm 5. Any questions? Now you don't really have to memorize this algorithm line by line. What is beneficial is that if you understand the algorithm, the idea behind the algorithm. Alright? But if you're stuck, then it is good to just follow the algorithm line by line. Okay, so any questions for now? So this brings us to the how do we form the decomposition then? Like I said at the start, to decompose any relation schema R into the decomposed schema that satisfies BCNF is very, very easy. It is actually trivial. You just decompose things into two attributes. You don't even need to decompose to one attribute. Two attributes is fine. Okay? But if you do this, there's no guarantee that it will be lossless join. There's no guarantee that it will be dependency preserving. So we need to be smarter here. And what we want to do is we want to try to guarantee as much as possible lossless join and dependency preserving. So can we do this? Can we decompose any schema such that we maintain this property? So unfortunately, lossless join is easy, but dependency preserving is not easy. There is no guarantee that what we are doing is going to preserve the dependency. So we cannot guarantee this. Okay? And the idea is this. The idea of the way to move forward is that we find one decomposition, we find one violation. So we have two cases. If you look at any relation schema R, you have two cases. One, well, R is already in BCNF and you're done, right? But if it is not, it means that you can find one violation. Choose any one of the violations, you do the decomposition based on that. Right? So that's why the algorithm 5 from before gives you one violation. So this comes from algorithm 5. So in fact, you can do any version of algorithm 5 as long as you can find one violation, you do the decomposition based on that. So this decomposition is then the main reason why this decomposition is lossless join. Because once you do the decomposition, you have the this. Okay? And then based on corollary 1, this preserves the lossless join. This makes it to be a lossless join decomposition. So once you do this, then you can either do recursion, right? So now you have two candidates. You have two candidates here, R1 and R2. You can do recursion, saying that, well, I need to check whether R1 is in BCNF, or I can check that R2 is in BCNF. Once you do all that, then everything, every single fragment will be in BCNF. And again, if you keep on doing this, every single fragment, if you combine them, it will be a lossless join decomposition. Right? Because each of these single steps split into two, and that guarantees to be lossless join. Okay, so you can develop this algorithm as a recursion, or you can do an iteration. If you do an iteration, you need to have a kind of a stack, either a stack or a queue, and then you just keep on putting to the back, and then just continue forward. Okay? So you have two possible ways to do this: either recursively perform this algorithm, or you put it into the queue, and then you keep on taking it from the queue, checking whether it's BCNF. If it's not, you split it into two, put both back into the queue, and then you check the next relation. Okay? The algorithm that we are doing here, algorithm 6, rely on the second method. We will be using a queue. So think of this as your queue. Right? You check until it's empty. While it is still not empty, you check whether you remove one element from the queue, you check whether it's in BCNF or not. And that is using the algorithm 5. There are two possibilities from this algorithm 5, and that is it is in BCNF. Okay, and then we're done with this relation. So we're just going to insert it into the result. Okay, now on the second part, on the second case, this one violates BCNF. So we find from this violation, we try to decompose in a lossless join manner. So now your queue expands. Your queue expands with 2 more relations. And then the process continues until the queue is eventually empty, and everything will be put into this result. There is a running number here, I equals to I plus 2, and that is just to make sure that each of these relations will have unique names. Okay, if you don't care about the uniqueness of their names, you can simply discard this line tag. Right? So yeah, this one is just to ensure that this will be unique, fresh name. So any questions? So that's algorithm 6. So what we're going to do is we're not really going to go through the algorithm step by step. We're going to use the essence of the algorithm to show you how it works. So let's say this one. The job here is to find a possible BCNF decomposition. And then you ask yourself whether it's lossless join or dependency preserving. Okay, so it will definitely be lossless join. Right, so you start with a single relation. So I'm doing the recursive way. I'm just going to choose any one of these. I'm going to decompose based on that. Okay, so at the simplest way, that's what I'm going to do. Now, of course, the violations can be many. Right? So I can always say that there are other kind of violation. I can say that AC to BC is a violation, or AC to B is a violation. Right? So this one definitely violates. This one definitely violates. But AC to B, well, this one is an F plus, and this also violates. Because AC plus is not the superkey. Okay? So just choose any one of those. So what I'm going to do is I'm going to choose this. By choosing this, what I will get is too far. Okay, so I try to decompose based on this. So what we're going to get at this point is R1 is going to be AB, right? So the other one will be some kind of intermediate, so let's use R2, which does not contain B. Okay, so A, C, D, E. And then I choose, so I've already chosen this, I already decomposed based on this, so I should not choose this anymore. So then the other choice will be just this. I try to decompose based on BC to D. Okay, so BC to D, well, this one doesn't actually work here because we don't have B. So we try to find another decomposition. Yes, AC. AC to D. AC to D is pretty simple because AC plus with respect to this F here is equals to A, you get B, from BC you get D. Okay? So, well, I say well, AC to D. Then this decomposition gives me R3, ACD, and this part without the D. So you get R4, A, C, E. Okay? Now you check this. This one, 2 attributes, definitely going to be BCNF. This one, 3 attributes. Then you check all the possible functional dependencies in FR3. You check one by one, and then you will figure out that this one is actually in BCNF. Okay, so you can stop here. BCNF, BCNF. And this one you can actually also stop here. Right? So if you find FR4, when you look at all the FD there, you will see that this one actually satisfies BCNF. Okay, so this is one of them. Okay, and this is the decomposition that I told you. This is the intermediate steps. Then the question is this one actually dependency preserving? So this particular one is actually not dependency preserving. And I can give you a counter example. Right? And the counter example is that this BC to D is not going to be preserved. Okay, so how do I show that this one is not preserved? Well, you look at FR1. The FR1 that I'm going to show you is that this one is consisting everything that is completely non-trivial. Okay, so I'm going to exclude everything that contains any trivial part. Okay, and then again FR3, if you only look at everything that is completely non-trivial, then you will get it. If you look at FR4, everything is actually trivial. Alright? And the reason why this is completely trivial is because of the presence of E. E here must appear in both left and right hand side. And once you have E, then it is basically mostly going to be the super key anyway. Right, so then you do the join. Once you do the union, you will get A to B and AC to D. You try to prove this by computing BC plus with respect to this. You get BC, you get BC. BC plus with respect to this is simply BC. You see that D is not there, so this one does not imply BC to D. Right, so any questions? So this one is one of the FD that is not preserved. Alright? So any questions so far? So this shows that if you follow the algorithm, then you may come into a decomposition that is not dependency preserving. Now the next one is something that will blow your mind, and that is if I do the decomposition differently, if I start with this, okay? So this is one violation, so I can always start with this. I get my R1 as BCD, my remaining one as A, B, C, E. Okay? If I do this, then I can do the A to B here, because again, A to B is definitely going to be violated. So then I will get R3, AB, R4, A, C, E. Right, now this one is going to be in BCNF, so if you check FR1 is going to be in BCNF. Trivially in BCNF, this one we say that from before, this is already in BCNF. Okay? So, the same algorithm, but if you choose a different violation for the decomposition, then what we will have is that somehow this is dependency preserving. Okay? So some choices may make it to be dependency preserving, and another choices may make it to be non-dependency preserving, even though we are using the same algorithm. Alright? And this algorithm is intended to be non-deterministic from the start, because line 3 just say remove some. This is non-determinism. Depending on which one you choose and which one the algorithm 5 gives you, what violation it gives you, there are many possible decompositions that you can get. Okay? So last semester, I had an algorithm that tries to enumerate everything that the algorithm 6 can find. I kind of regret it because for the assignment 4, for some weird reason, I get 14,000 possible decompositions. And yeah, then I have to check based on this whether your answer matched any one of them. And that was a nightmare, even though it's fully automated check. So yeah. So the same algorithm used with a different starting point, starting violations, can give you one of them dependency preserving, the other one non-dependency preserving. Now what it also means is that there are some cases where you can never get dependency preserving decomposition. Okay? I can give you one of the example later, but in particular you can always find some possible non-dependency preserving. So all algorithm 6 will find will be non-dependency preserving. Okay, so there is a possibility for that. Okay, so let's look at the properties of this. The property of the algorithm 6, the most basic property is that it will definitely terminate. Okay, and how do we know? You look at the recursion. The recursion will always produce a relation that is smaller because it is kind of a decomposition. Right? And because eventually it gets smaller and smaller, eventually everything will eventually be in BCNF4, where at the worst case, everything will be 2 attributes. Right? So that's the worst case. If you keep on running this, the recursion, eventually all the attributes in the fragments will be only 2 attributes. Okay, so eventually it will stop. We don't know how long, but eventually it will stop. Right, so that's the first property. The second property is that it will always be lossless join. Okay, it will always be lossless join because we find a violation that is completely non-trivial. We do the decomposition based on this. And that means that we can use corollary 1 to justify that this decomposition will always be lossless join. Right? So 2 properties, and again, it may not be dependency preserving. This is an example where you can never get dependency preserving decomposition. Okay? So this particular problem has a property that it is either not in BCNF or it will never be dependency preserving. Right, so that's the 3 properties. Okay, so it will terminate, it will always be lossless join, but it may not be dependency preserving. Okay? If you use algorithm 6. If you use any other algorithm, there's no guarantee for anything. Alright? So this example, I can expand it more. Right. So this is a possible use case on why the example is not going to be BCNF. Okay? So this is a possible real problem. So every course must be managed by exactly 1 professor. Right? That is a very standard constraint. Okay? If you need this constraint, then you need to have this functional dependencies of course. Okay? And then there is another kind of a very normal constraint is that a professor cannot teach 2 courses at the same time. Which means that if you have a professor at the time, you know what kind of course he will be teaching. Okay, you can even know whether he's not teaching anything. Right? So if you map it back, this is A, this is B, this is C, then you get back that previous schema. And this cannot have both BCNF and dependency preserving. Okay? Even though we start with 2 totally normal constraints. Okay, and the reason why this is not in BCNF is because this is the key idea. You have an overlapping key. Once you have an overlapping key, it is found that you can never get a dependency preserving decomposition for BCNF. Okay? So what you can do now is you can look at your ER diagram check whether you have a possible overlapping key or not. If you do, then there's a high likelihood that you will not be able to get BCNF. So yeah, so the BCNF is very, very strong. So because it is very, very strong, we get this this property that given this algorithm, or basically any kind of algorithm at all, there is a possibility that you can never get a dependency preserving fragment. Okay? So we need to have a way to relax this condition. We need a way to say that this R, A, B, C, you do not have to decompose it further. Okay? If you allow R, A, B, C not to be decomposed further, well then it's definitely not going to be BCNF, but we may get another normal form that still preserves dependency. So that is the essence of third normal form. The main difference between the BCNF and the third normal form is that you have these additional attributes, you have this additional property that the right-hand side can be a prime attribute. Okay? And to see why this kind of gives you the non-overlapping, this handles the overlapping part. Look at this. B is part of the key. Because B is part of the key, that means there must be some non-trivial dependency. Right? Because there's non-trivial dependency, that non-trivial dependency is most likely going to include the other key. Okay, so this is the part where it gives you the overlapping condition. Okay, so the C is the overlapping condition, the overlapping key. All right, and the sign for overlapping key is that you have a functional dependency, non-trivial functional dependency, that the right-hand side is actually a prime attribute. Okay, so that's what we want to allow. We want to allow the right-hand side to be a prime attribute. So again, everything else is almost the same except for these little changes. So when you want to check, you need to also check that A is a non-prime attribute. Okay? The definition for the decomposition is also the same, but everything is just changed to 3NF instead of BCNF. Okay? And if you're going to check, you check whether it violates the 3NF instead of the BCNF by checking this additional constraint. All right, so again, everything is roughly about the same. So let's have an example, a little bit of exercise. Is this in 3NF? Okay, so our previous answer was that this one is in BCNF. Now, everything that is in BCNF is definitely going to be in 3NF. Because if it's in BCNF, you have a stricter condition. Now you relax the condition, so everything that satisfies the stricter condition is definitely going to satisfy the more relaxed condition. So if this was in, oh, this one wasn't in 3NF. It wasn't in BCNF. Oh, right, because of B. Okay, so yeah, this one is not in 3NF because B is not prime attribute. B is not prime attribute because the only key is ACE. Right? So again, this one, if you choose this also violates. So the next example, you have, okay, so let me think about it before I give you the wrong answer again. R2, so what was the FR2 that we got before? Let's check. ACDE. This is AC to D. Okay, so you have AC to D. AC to D. Now, is D part of the? Is D part of? So you have AC to D. The question is D part of the prime attribute? So the key here. So if you want to find the key, you copy this to this ACDE. You look at the key. Sorry. AC to D. And ACE. Right? So it should not be in QNF. Oh. So this should still be the wrong answer from before. This should not be in QNF. Okay, yeah, so this is a lesson on why you should not copy paste the slide. So you have AC to D, and then you have so you need to look at this. This one, AC is not, so AC is not, so this is non-trivial, AC is not super key, and D is not prime attribute. Alright? So ignore this. This is not in 3NF because of this. Okay? So any questions? Right, so if you look at this, the keys are definitely ACE. You need E as part of the key. You definitely don't need D as part of the key. Right, so ignore this. You consider AC to D, the one, non-trivial. So this is in FR2. Second, AC plus not equal to R2. And third, D is not in prime attributes of R2 with respect to FR2. Okay, so this is the reason why this one is not in 3NF. Not in 3NF. Okay, so any questions? Right, so remember this example. This example is definitely not in BCNF because it wasn't in BCNF. So the question is it in 3NF? Okay, and this is exactly the reason why we need the 3NF because we have the overlapping key. So based on our analysis before, the two keys are AC and DC. They overlap on C. If you consider this, then B is a prime attribute. Okay, and if you consider this, then DC is a super key. And also A is a prime attribute. Okay, so this is in 3NF. And this is the reason why we need the 3NF, because the BCNF is too strong. Okay, so any questions? So again, can we have a decomposition that is in 3NF, and again, this is trivial. Make sure that every fragment has exactly two attributes. Okay? So based on lemma 3, every fragment that contains two attributes is definitely going to be in BCNF. Okay? And because 3NF is a relaxed version of BCNF, that means everything that is in BCNF is definitely going to be in 3NF. So lemma 3 is expanded to also include 3NF. So again, now what we want to do is something smarter. Can we guarantee lossless join and dependency preserving? Is there a way such that we satisfy 3NF while still have lossless join and dependency preserving decomposition? And the answer is actually yes. We can guarantee both. Right? So to see why it guarantees both, we need to look at the idea of what we want to do with the decomposition. How do we form the decomposition? So the previous method, the method of decomposing, so we found one FD, one violation, and then we do the decomposition, right? And then we may find another FD, FD2, we find another decomposition, right? So this is one possible method, and then I'm sure you can always extend this to 3NF, but what I'm going to show you is something simpler. It is what we call as a constructive method. So instead of finding violations, decompose, find violations, decompose. Again, what I want to do is I want to construct from the ground up all the fragments that was definitely going to guarantee that I'm going to get lossless join and dependency preserving. So the main idea here is that you look at every single functional dependency. We want to make sure that it satisfies at least one of the 3NF property. Okay? So how do we ensure that can we ensure that there's no such subset of it that violates all three? Okay, so that's what we want to do. If you want to construct the 3NF from the ground up, we need, when we consider any kind of functional dependency, we want to ensure that for any subset of the left-hand side, we can never violate the 3NF property. And there is one simple way to ensure that, and that is the minimal cover. Okay, minimal cover guarantees that all the FD is going to be does not have redundancy, right? Which means that it is guaranteed to be completely non-trivial. Right? So again, first, it's completely non-trivial. So this part is completely non-trivial. And again, the other thing is that you can never have this. Okay? You can never have this particular property. So A prime cannot be a super T because we say that there's no redundant attributes in any of the FD. Okay? So you can never decrease the size of the left-hand side. Okay? So if you start with a minimal cover, then the constructive algorithm to form 3NF is actually very, very straightforward. You look at the minimal cover, you look at every single functional dependencies in the minimal cover, you make that to be a relation. Okay, so that's the main idea. And this is the algorithm. Okay, so you start with a minimal cover. So there's no redundant attributes, there's no redundant FD. And because of that, if you apply the union rule, okay, so the union rule is actually very, very important here because you do not want to have AB to C and AB to D separately. Okay? You do not want to have this. I mean, obviously you can, but you do not want to have this. So what you want is that you want to combine these two into AB to CD. Okay? So we try to be minimal in our number of tables as well. For these two, you need to have R, A, B, C, and you need to have R, A, B, D. But if you start with this, then you have R, A, B, C, D. So you start with the minimal cover. You do the union rule to combine all the FDs with the same left-hand side. You get this, G. And then you create one by one. So this is the constructive algorithm. So each of this comes from the minimal cover. It is guaranteed to be, so each of this is guaranteed to be completely non-trivial. Okay? So once you create all the relation schema consisting of this, there's one more thing that you need to do, and that is you choose one key. Why do we need a key? Now, think about it this way. If all your, you have the A, B, C, D, E, if this is your relations, and you only have A, B, A to B, and B, C to D, and you form your tree and F based on this 2, then you are actually missing the attribute E. Okay? You're missing this attribute E. But if you miss this attribute E, you cannot get a correct decomposition. It cannot be a valid decomposition. Because when you union all the attributes, you're missing E. To get back the E, we have a guarantee that E does not appear in any right-hand side. So E does not appear in any right-hand side. This guarantees that E will always be in the key. So the key ensures this. The key, the inclusion of any one of the key ensures that this becomes a valid decomposition. Alright? And in fact, the key here, the selection of the key here, by including one of the key, you also guarantee that it becomes a lossless join decomposition. Okay? Now, the other thing that we guarantee here was the dependency preserving, right? Dependency preserving is guaranteed because each of this is going to be preserved by the Ri. Okay? That is how we form it. We form the tree and F this way because we want to have a dependency preserving decomposition. Right? And think about it this way. Each of these functional dependencies is definitely going to be preserved because it appears fully here. It is part of this projection. So you have AI to BI is definitely going to be in FRI. It is definitely going to be preserved. Okay? So now you have an algorithm to compute the tree and F that guarantees lossless join and dependency preserving decomposition. Okay? So this is the main properties. The algorithm will definitely terminate because there are limited functional dependencies, and again it's the minimal cover. It is a valid decomposition because any attribute that does not appear in any functional dependencies is definitely going to appear in all the keys. If you choose one of them, then all the attributes will appear. Okay, the proof for this is more complicated, so I'm just going to omit. But basically, the intuition is that the path will always involve the key. So the last one is that it's going to be dependency preserving because each of this is going to be made into one relation. So AI to BI is going to be in FRI. If you union all of them, you will definitely get back the minimal cover. Alright? So yeah, so those are the properties that we can guarantee. Now, however, if you need the best kind of decomposition, you still need to check whether there are any BCNF decomposition that may give you dependency preserving decomposition. Okay? You should not go directly to 3NF. You should always try to start with BCNF. Okay? Because like what I said before, there's a possibility that based on the choice of the the violation that you choose, you may actually get a dependency preserving decomposition. Now, the property that is not nice about this tree-NF is that, unfortunately, this is again non-deterministic. How do we know? Well, minimal cover algorithm is definitely non-deterministic. Okay? If you look at the minimal cover, you need to remove one of the redundant attributes. If there are multiple redundant attributes, there's a possibility that you may not remove all of them. So based on those that you remove, you will get a different minimal cover. So again, the same thing with the redundant FD. Based on which FDs you choose to remove, you may get a different minimal cover. From the different minimal cover, you may eventually get a different tree-NF decomposition. Now, there is one part about the tree-NF that I forgot to talk in detail, is that this. So now that we know that it is going to be valid, it is going to terminate, it is going to be lossless join, it is going to be dependency preserving, then if you somehow have A to B, okay, so capital A to capital B, and BC to A, this means that you don't need to keep both, right? So if this one forms R1 AB, this one forms R2 A B C. You do not have to keep both. You just have to keep one of them. And which one you keep is the larger one. Okay? So the condition here, if it is a subset of anything else, you can remove that. So R1 here is a subset of R2. Then you can remove this. And that includes the key. You may eventually remove the key. But if you remove the key, it means that the functional dependency, the set of functional dependencies that you have in the minimal cover will contain all the attributes. And you don't even need the key after that. Okay? So yeah. So this is the summary. In the end, we get into, this is the last week summary. I'm going to get the new summary. Yes, I forgot to do this. But our final form is three algorithms. We have algorithm 5 to check for BCNF violation, algorithm 6 to do BCNF decomposition, and algorithm 7 to do tree-NF decomposition. Okay? The algorithm 7 is what we call a constructive method. You build it from the ground up and it will satisfy all the properties. The algorithm 6, you basically find one possible decomposition. Both algorithm 6 and 7 are non-deterministic. Okay? So there's a possibility you need to check some other variants to actually come up with the lossless join and dependency preserving decomposition. So, any questions? Right, so if there's no questions, then I'll see you 2 weeks from now. Or if you're in my tutorial class, I'll see you on Tuesday. Now, this one has the BCNF decomposition and the tree-NF decomposition. So unfortunately, this BCNF decomposition is the algorithm for BCNF decomposition is actually quite stupid, because if you look at this one was the non-dependency preserving, right? For this particular case, it will actually get the non-dependency preserving decomposition, right? So I do have a separate algorithm, which I didn't include here, is to find all the possible BCNF decomposition. And the reason why I'm not including it here is because it takes very, very long to compute. Okay? And in fact, I have two versions of it. So if you want to do it on your own, there are two ways to get all the possible decomposition. One is that you first get all the possible decomposition. How many possible decompositions are there? The number of attributes, choose 2. That's all the possible fractions. Okay? And then you do permutation on them. So, in particular, it's the factorial of n choose 2 at the worst case. That's why it's kind of takes too long. I also have a non-deterministic version of this, but it is very, very non-uniform. That's why I don't rely on it. Somehow the random number generator is pretty bad. So yeah, the BCNF violation check will actually give you exactly the same thing. So this is one. This is one possible violation. It may not be the best violation, but it is one of them. So yeah, so the 3NF decomposition actually gives you a BCNF. Right? So sometimes the 3NF decomposition gives you this one was the second. This one was the second decomposition. BCD, ABACE. BCD, ABACE. But the reason why the 3NF decomposition algorithm gives you the BCNF decomposition is because in the first place, there is one possible step. There is one possible application of algorithm 6 that can give you dependency preserving decomposition. Right? So, yeah. And then you just have to check whether this one satisfies BCNF. So if you want, there are multiple ways to come to that conclusion. Alright, so if there's no more questions, then I'll see you next week. Oh, 2 weeks from now, sorry.
这没弄说。
如果你是个老师的话，就会老师的话，如果你是个老师的话，就会变成teaching module，然后 module 是什么？